Hey everyone, and welcome to today's Explainer. I am absolutely thrilled to guide you through this journey today. If you're the kind of person who's always curious about the how and why of the world around us, well, you're in exactly the right place. Today, we're taking a fascinating look at the theory-to-practice pipeline. We're going to be connecting high-level, foundational scientific theories directly to the hands-on, everyday realities that you can actually see and touch. We'll be pulling from some foundational science texts to see how the macro rules of the universe align perfectly with microscopic biology and everyday practical physics. It's going to be a fantastic ride, so let's get right into it.
Okay, let's dive into this. Here's our roadmap for today's Explainer. 1. The scope of science. 2. Solving problems systematically. 3. Exploring the microscopic world. 4. Quantifying the physical world. And finally, 5. Forces in action.
Starting right off with Section 1, the scope of science.
If we really want to understand our universe, we've got to start with physics. You can think of physics as the mother of all sciences. The word itself actually derives from the ancient Greek physikos, which means knowledge of nature. It's the branch of science that studies matter, its motion, and its behavior through space and time, along with energy and force. But listen, this isn't just abstract math, right? This is the very foundation of modern society. Without this fundamental understanding of matter and energy, we wouldn't have the technologies we literally rely on every single day. The discoveries in physics are exactly what gave us television, computers, smartphones, aircraft, and advanced medical instruments. It is the literal engine of human progress.
Now, since the universe is, mind-bogglingly vast, scientists have categorized physics into distinct branches to better organize our understanding. Just look at the sheer spectrum here. We go from the absolute extremes of celestial objects in deep space with astrophysics, right down to the internal structure of our own planet with geophysics. We also have plasma physics, looking at the ionized state of matter, and then we've got the classics that govern our immediate physical reality. Things like mechanics, which deals with motion and gravitation, and thermodynamics, which focuses on heat, temperature, and how they relate to energy and work. From atomic nuclei all the way up to large-scale galaxies, these branches cover the whole shebang.
And this brilliantly illustrates the diverse toolkit of the physicist. We've got classical mechanics, represented by the pendulum, atomic physics, and magnetism. But how are these tools actually used? Well, the scientific community is generally split into two vital camps. First, you've got your theoretical physicists. These are the scientists who observe nature, notice the mysteries, and use mathematical approaches to present theories that fill in missing information. But, as we know, a theory is only as good as its proof, and that's where experimental physicists come in. They're the ones in the laboratories, designing physical tests to prove or completely disprove those theoretical models.
Which brings us to Section 2, solving problems systematically. So, how do we actually solve mysteries in the real world? We use the scientific method. This is the ultimate problem-solving framework. It all starts with a spark, formulating a hypothesis. This is essentially an educated guess about how something works based on your initial observations. Next up, you conduct experiments to gather results and observations, and you have to detail every single piece of data during this phase. Finally, you develop a final conclusion. This is the critical step where all the results from the experiment are analyzed to see if they verify that initial hypothesis.
So, the crucial point is seeing how this works in a real-world application. Let's look at a historical, literal life or death scenario, malaria. Scientists hypothesized that a specific parasite called Plasmodium was the cause. To test this systematically, they didn't just look at sick people. They gathered results by checking the blood of all the malaria patients. That was their experimental group. And they also checked the blood of healthy persons, which served as their control group. And the result? Plasmodium was found in the experimental group, while the control group was completely free of it. This clear, systematic comparison allowed them to definitively verify their hypothesis in the conclusion.
Let's zoom in a bit for Section 3, exploring the microscopic world.
I want you to visualize yourself sitting at a lab bench right now. We're going to prepare a human cheek cell slide. It's incredibly straightforward. First, you place a drop of water on a clean glass slide. Then, using a clean earbud, you gently wipe the inside of your cheek to collect a moist film. You smear that film right onto the water droplet on your slide. Next, you gently cover it with a cover slip and add a drop or two of a stain, something like methylene blue, to the edge of the slip. Grab a tissue to soak up any excess dye, and boom, you are ready to observe your own cells under the microscope, moving from low to high magnification. It's hands-on science at its absolute best.
Now, if we were to zoom in even closer on those cells, we'd find a massive flurry of chemical activity, all driven by enzymes. These are biological catalysts that literally make life possible, and they are highly organized. As you can see, there are two main categories here. Intracellular enzymes do their work strictly inside the cell. Examples of these include ATPase and cytochrome C reductase. On the other hand, extracellular enzymes are secreted to work outside the cells. Classic examples here are pepsin and lipase, which are the ones that help break down materials in our digestive tracts.
But what is truly amazing about these chemical workers is their absolute precision. Enzymes are incredibly bond-specific. They don't just go around breaking down everything they touch. They're specialized for particular structures. For instance, proteases are enzymes that catalyze proteins, and only proteins. And lipases, they act exclusively on lipids, which are fats. Because of this bond specificity, a lipase enzyme will strictly target and act upon an ester bond found in lipid and fat substances. It's like a perfect biological lock-and-key mechanism. A lipase is never going to touch a protein, and a protease will never touch a fat.
Let's move to and see how this builds into Section 4, quantifying the physical world. Because whether you're counting cheek cells or measuring the speed of a galaxy, we all need a universal language. And that language relies on the concept of a physical quantity. In science, a physical quantity is any property of a phenomenon, body, or substance that can be quantified by measurement. To communicate this accurately, it must always be expressed as a combination of two things: a magnitude, which is the actual number, and a unit, which is what gives that number meaning. Think about it like this. If I tell you to walk 5, that means absolutely nothing. 5 steps, 5 miles. You need a magnitude, the number 5, and a unit, miles, to actually give it meaning. Whether you're working with fundamental quantities like length and mass, or derived quantities like velocity and density, science fundamentally falls apart without exact measurement and clear units.
And finally, Section 5, Forces in Action.
All right, now that we know how to measure things, let's put it to work in the real world. To really understand forces, we often look at friction. Here's a classic laboratory setup to experience it for yourself. To do this, you'd need a wooden block, a spring balance, which measures force in newtons, some connecting strings, and a few slotted weights. By pulling the block across a wooden table, the spring balance stretches out, and that gives us a precise physical quantity of the frictional force that's resisting our pull.
Now, what's really interesting about this slide is how we change just one variable at a time in this progression. Following that scientific method we talked about earlier, first you put a 1 kilogram slot on the wooden block, pull it, and note the reading. Next, you replace it with a 3 kilogram weight, pull, and note the new reading. Finally, you increase it to a 5 kilogram weight and pull again. By carefully recording these observations, you mathematically prove that as the mass of the object increases, the physical force required to overcome friction across that wooden table increases proportionally. It is elegant, it's measurable, and it's completely undeniable.
But here's the best part. These physical forces don't just live in some dusty laboratory. They are in your home, right now. On the left here, we have a laboratory cream separator, which is a device that spins rapidly to separate denser materials from lighter ones using physics. And on the right, that's a modern washing machine with a built-in dryer. When your washing machine enters its spin cycle, it's utilizing the exact same physical principles as that cream separator. It rapidly spins the wet clothes, forcing the water out through the drum and drying your laundry. Physics is literally doing your chores for you.
So, from the massive laws of thermodynamics to the highly specific ester bonds targeted by lipase enzymes, and from a simple spring balance on a lab bench all the way to the washing machine in your laundry room, it is all deeply, beautifully connected. The scientific method allows us to observe, quantify, and utilize the rules of nature to better our world. So I'll leave you with this thought. You are walking, breathing proof of these physical laws in action. The next time you do a load of laundry or even just digest a meal, ask yourself, what other unseen scientific pipelines are running in the background of your daily life? Stay curious, everyone, and thanks so much for joining me on this explainer. Keep exploring.